In this video, we are going to see another circuit design example. So, this is the problem. We have to design a system that have to detect when some processing units in a microprocessor are in some states. Okay, so basically what we are asked to do is to design a small module that goes inside a probably big and very complex microprocessor, and in this microprocessor there are several processing units, okay, P1, P2, P3, P4, and sometimes these units may become busy. And what we have to do is to design a module that takes information from all those processors, okay, and tell us when my whole system is busy or not, okay. So the inputs to my circuit are 4 signals that go from P1 to P4, and the output should be activated when some conditions are met, right? So we are going to name the output. Our output will be B, okay, and we will consider that my system is busy when B is equal to 1, okay, and it's not busy when B is equal to 0, okay. With this information, we also consider that any input signal to my system, Pi, indicates when the corresponding unit is busy or not. We have to make it very clear what it means for us. So 0 will mean also busy, 1 will mean busy, and 0 will mean not busy, right? So now with this idea, I have started doing the formal specification of my system, okay? So I now have the well specified what are going to be the inputs and outputs of my system. There are 4 units that I have to consider. So we have a block with inputs P1, P2, P3, and P4, and we have an output we call B, okay? And the inputs and outputs indicate information with digital signals like here. Okay, now to express what my system must do, I can, and to simplify the expressions, to build a circuit and so on, we need to get information into a kernel map. So some people find it easier to put information in a truth table. So going to truth table from the specification, then moving the information to a K-map, and from here doing the simplification and so on and so forth. But actually there's no real reason to use a truth table, okay? You can do as you prefer, but most times you can copy the information or to directly to the kernel map, and so you already have it there, because the kernel map actually is just also a kind of truth table, only that the information is sorted in a slightly different way. So we draw our kernel map. More or less like this. I'll make some corrections here. Great. So we have our inputs now are P1, P2, P3, and P4. And what we are going to do is just move the information from the description of the problem to our kernel map. Okay. So it says the system is considered busy when any of the following conditions is met. It says any condition, okay, and it's considered busy, which means I have to make B, the output of my circuit, to be 1 when any of these conditions met. So I will check one by one, and it will tell me when the function is 1. So the first condition is that P1 and any other unit are busy. It means that whenever P1 is busy, so whenever P1 is 1, it is these two columns here, and any other unit is also 1, so the system should be busy. So in this case, using this column, P1 is busy and P2 is also busy. So the condition is met in all these columns here. Okay. In this column, P1 is busy and P2 is not busy. So the condition is only met when some other units are busy. This one, and this one. So, okay, all these ones are extracted from the first condition. Now, the second condition says P2 and P3 are busy. When P2 and P3 are busy, then the system should be signaled that it's busy as well. It means that whenever P2 and P3 are 1, the output B must also be 1. So I find the cases where P2 and P3 are 1. P2 is 1 in these two columns, and P3 is 1 in these two rows. So all these cells correspond to that condition. P2 and P3 are both 1. We already had ones here, so I complete the block here. Now the last condition is that P4 is busy and neither P1 nor P2 are busy. So I consider my system busy when P4 is busy. It is these two rows here when P4 is 1, but not at the same time P1 and neither P1 nor P2 should be busy at the same time. So this will be 1 all the time except when P1, okay, or P2 are also 1. It eliminates all these cells here. P2 is 1 here, P2 and P1 are 1 here, P1 is 1 here. So it only leaves these two cases here, okay? P4 is 1, nor P1 nor P2 are 1. Okay, so this hopefully is what my circuit have to do. In all these conditions where there's a 1, the output will be 1, the system will be considered busy. In any other condition, even if some of the units in my processor are processing, are busy actually, but the whole system is not considered busy, probably because it still have enough units available and that are powerful enough to do some extra job. Okay, but whatever it's useful for, we just design our part of our system. So now we have a representation, a formal representation of my system. Now I can manipulate it to obtain a circuit. So let's go to the details on what's the circuit we have to obtain. It says design a minimum two-level circuit. Two-level is what we will do all the time because it's based on sum of products, products of sum, and so on. Two levels plus inverters. It means it doesn't, the two levels thing doesn't count the possible inverters that we will need, okay? And it also says that inputs are in single rail. Single rail means that these outputs are right to my circuit, but we don't have the complements available, because sometimes it happens that because the way the circuits are designed, these inputs may be available also already complemented, so we don't need to use inverters to complement them. But in this case, these are single rail. It means I have the input alone. If we have inputs in double rail, we have the inputs and also the complements, so we don't need to use inverters. Okay, in this case, we do need to use them. Okay. Also, the problem says design a minimum two-level circuit, because we need a minimum. It doesn't say what type of structure we should use. We must try to minimize the expression using sum of products and products of sums, and use the one that is more simple, that has the lower cost. Okay, so we'll do our minimization first as a sum of products. Okay, so I find the prime implicants. Starting with this one, I have a implicant here. I look for the adjacencies. This is adjacent to this one, and there are no more adjacencies. Okay. Possible adjacent implicants to that one could be this one. Okay, or it will be the one on top. Okay, this one. All these maybe would have been adjacent implicants to the one in green here, but oh yes, I have. Okay, but I don't have this, or this was I have written by myself. Okay, we don't have min terms here. Okay, to complete this adjacent one, nor min terms here to complete this adjacent one. Okay, so it's this implicant is already a prime implicant. Okay, now we start with this one, for example, this and this. These are two. This is an implicant. This adjacency we don't have. This one we don't have. The one on the right we have. So this would be a more simple prime implicant, and that's it. This cannot be simplified anymore. So this is another prime implicant. Okay, we have already done some examples with this, so I will not go much into the details, but this will be another prime implicant starting here. These two together with these two. If we start here, we have also these two together with these two, so this is another prime implicant. And these two are also have this group here. Okay, so this could be another prime implicant as well. And I think we are finished doing our prime implicant solution. Okay, so in this case B, I could be equal to, so this is essential, this one is essential, this one is essential as well, this one is essential as well. So using these four essential prime implicants, 1, 2, 3, and 4, we have all my function covered. So there are some prime implicants, like only this one that I don't really need to include, okay? Only the essentials. So this one here is P2 complemented P4, or this one here is P2 P3, or P1, P3, and the one here is P1, P2. Okay, so this is the minimal size sum of products. We can estimate the cost here. We have 1, 2, 3, 4 terms plus 1, 2, 3, 4, 5, 6, 7, 8 literals. And because we are using single rail, we have to build the complements. We have one complement here. So the total cost for this implementation could be 13, right? Okay, now let's go with the option of the product of sum. Okay, I will copy my map because it's always better than doing in the same map. Okay, and we will go and remove what we have already done there with a little care, yes, to use the same map again. Okay, now we will use this to simplify our function as a product of sums. So now we start with the zeros. If we prefer, you can write now the zeros explicitly. Okay, the zeros are here as well. We have it written them just to have the map a bit more clear. But now that we are going to map the zeros, it may be a good idea to write them. We leave the ones there. And now we start again. So this 2 is a prime implicant, no adjacencies, so this is a prime implicant. Here, this 0 as well, have a 0 here. This is also an implicant, no adjacencies, so this is another prime implicant. These 2 zeros are also another prime implicant. And this 0, the only adjacency is the one on top, so this is also prime implicant. From this is essential, this is essential, this is essential, and by using these 3 implicants, actually 1, 2, and 3, we have all the max terms covered. Okay, so B can be expressed using those. So I'll start with this one, which is P1 plus P2 plus P4. This one, now this one is P1 plus P2 complemented plus P3. And the last one is this one on the sides, which is P2 equal to 0. So we have P2 plus P3 and P4 is 0. So P3 plus P4. Now the cost for this implementation is we have 1, 2, 3 terms plus 1, 2, 3, 4, 5, 6, 7, 8, 9 literals, and we have to do one complement. So the cost is 13 as well. Okay. So as you can see, even if this expression has more terms, these are 4 terms, okay, and this expression has 3 terms, the cost is actually the same because this has fewer terms but more literals. Okay, this has more terms but fewer literals. Okay, so we can say that the cost is similar, so we don't should prefer one or another. In any case, because this one has fewer terms, we are going to use then this one for the implementation, okay? The sum of product. So we need a first level of OR gates. We will have then 4 OR gates, 3 and 4, to do all the terms, and then we will make the product of all those terms using AND gates. Just one AND gate. It will give my function B, and now we start doing the connections. We have P1 here, P2 here. We leave enough room here because we will probably have to make connections for the other gates. So it's good to plan a bit in advance how your drawing may be. And the other one will be P4 here. Great. Next one will be P1. I take P1 from here. P2 complemented, I will need an inverter. So I will use something like this. I use an inverter here. Okay, so I have P2 complemented here after the inverter. Now the next one is P3. I left this space here to connect P3. Great. And I think I have used one gate more than necessary. Okay, it's only 3 terms. Okay, so it's finished. The last one is P2. So I'll take P2 from here. P3, I'll take P3 from here. And P4 again. I have already used the corners, yes, not to make too many connections. And that's it. Okay, that will be the optimum, an optimum or an optimal, one of the optimum or lowest cost implementations for our interesting device in our very advanced microprocessor. Okay, oh, sorry. Thank you.